right, so let's maybe complete theorem 5 that we started. So the statement would likely be clear, but let me quickly review the statement. So the statement is saying let W be a subspace of a finite dimensional vector space of vector space V. Okay, so V is finite dimensional, and we're taking W to be a subspace, right? So this is a vector space. V is a vector space, and we take a subspace W. Now the claim is that any linearly independent subset Wi of W is going to be finite, and it is going to be part of the basis of W. Okay, so every linearly independent subset of W is going to be finite, and is going to be part of a finite basis for W. All right. So let's see how we can prove something like this. Suppose that S0 is a linearly independent subset of W. Okay. So suppose, okay, I was writing W, let's just call it S0. Okay, so S0 is a subset of the vector space W. I think it sort of also makes sense because I think they're using V and W for vector spaces and S for set and basis and so on. Right, so S0 is a linearly independent subset of W. So the first note is that if S is a linearly independent subset of W containing S0, then S is also a linearly independent subset of V, right? Because linear independence is the same, right? So if it's a subset and it is linearly independent, then it'll also be a subset of V and continue to stay linearly independent, because linear independence has nothing to do with the bigger set that S is a part of. Okay. So this is the first note in general. The second note is saying the following. So since V is a finite dimensional since V is a finite dimensional subspace, S contains no more than dimension of V elements, right? So this we already established because we said that at most the number of linearly independent vectors that exist as a subset of S, as a subset of V is going to be of dimension V, right? This was, let me see if I can pull the exact statement. Right, so this is the statement that no subset V that contains fewer than n vectors can span, any subset of V that contains more than n vectors is linearly dependent. Okay, so if it's linearly independent, then the size would be at most n. So that was is a consequence of corollary 2. So let me write that. This is a consequence of corollary 2. Okay, and now the strategy is that we extend S0 to a basis for W. Okay, so we know that the size, the number of elements in S0 is at most dimension V, and we know that this is also going to be a linearly independent subset of V. Okay, right. So now S0 spans, if it is the case that S0 already spans W, then S0 is a basis for W, right? And we don't have anything to prove, because we were saying that it is part of a finite basis of W, but if it is the entire basis, then we're done. So this is okay. And the other case is that if S0 does not span W, right, then one can use the previous lemma. What was the previous lemma? The previous lemma was this, right? It was saying that one can add this vector beta, right? I mean, you can check the recording for the previous lecture. This is just a continuation. So in the previous lecture, or in the lecture we just had, we said that one can add the vector beta to the set S, and it will stay linearly independent as long as beta is not already part of the set S that we started. Okay, sorry, not already a part of the span of the set S that we started. Okay, so, oops. So then coming back, what do we have? We have that if S0 does not span W, okay, then the preceding lemma says that, using the preceding lemma, we can find a vector beta 1 in W such that this set S1 is going to be linearly independent, right? Because so we have so S0 is a strict subset, right? Because it's not spanning W. Oh, sorry. the other way. Span of S is a strict subset of W, right? So there exists some beta 1 in W such that S1 equals S0 union beta 1 is independent, right? And this is coming from the lemma that we had because of the lemma, right? So this is fine. So therefore one can always find a vector which would satisfy this property. Now, if this new vector, this new set S1, it spans W. So if span of S1 equals W, then we are done, right? Because that's what we wanted to argue, that one can, that S0 forms a part of the basis for W. So this we've done explicitly. If it doesn't happen, we can apply the lemma again and obtain vector beta 2, right? Because then again, span of S1 is strictly smaller than W. So that would mean there exists beta 2 in W such that S2 defined as S1 union beta 2 is linearly independent, right? Again, because of the same lemma, right? And one can continue like this and then and basically argue that you would eventually be able to make it. Why? How do we know that this will stop? We know this would stop because there are at most dimension v many vectors, right? That we can have in a linearly independent set, because the dimension of W is known to be finite, right? So this procedure can only run dimension v many times because we are adding linearly independent vectors to a set, and there's only these many that are possible, and eventually it will therefore span the set. Okay, so Sm at some point will be able to span the set, and that is the basis for W. So that is the proof. Okay, I hope that was clear. Now let's move on to a corollary of this result. So the corollary says that if W is a proper subspace of a finite dimensional vector space V, then W is a finite dimensional subspace, and the dimension of W is at most the dimension of V. Okay, so let's look at this again. So if W is a proper subspace of V, okay, so these are spaces, this is a subspace, okay, and we have that this is finite, then this implies that dimension of W is going to be strictly smaller than dimension of V. So how do we see this? So suppose that W contains a non-zero vector alpha. Okay, so alpha belongs to W. Then by theorem 5 and its proof, we know that there is a basis of W containing alpha which contains at most dim V elements, right? Okay, so theorem 5, what was theorem 5? Let's see. So theorem 5 is the one that we just proved, right? That if you have a vector in the subspace W, then one can complete it into like being the basis for W itself, right? So we're doing something similar here. We are saying that suppose W is the subspace, and you are given a vector in the subspace, then one can actually make a basis for that spans W, okay, and it has at most dim V elements. This is fine. That also contains alpha, right? So this is fine. So this statement should be okay. Now we can therefore conclude that W is finite dimensional itself, and the dimension of W is at most dimension of V. This is essentially a consequence, right? Okay. Okay, and then W is a strict subset of V, right? We know this, and so there has to exist some beta in V which is not in W. So there exists beta in W, but beta is not in V. That's what it means to be a strict subset. Now, adjoining beta to any basis of W, we obtain a linearly independent subset of V. Okay, So now if we add beta to the basis of W, okay, what we get is a linearly independent subset of V. Okay, and so the union, right, so I think we saw this more clearly somewhere. Right, so it's basically the same lemma, right, that the set you obtain by joining beta to S is going to be linearly independent, right? So we proved this, essentially the same statement, okay? So here S is a linearly independent subset, and we are going to add a vector beta that is in the vector space, but this beta is not in the span of S, right? So this is exactly what we're doing here. We have a vector beta that is not in the subspace. Or did I write it the other way around? Oh, sorry, I had to write it the other way around. It's not in W, but it is in V, right? So this vector beta is not in W, but it is in the bigger space. And if you take the union with the basis vector, okay, this is a subspace, then what you get is going to be a linearly independent subset of V. And so what does that mean? That it means that the dimension of V is at least the size of beta union basis of W, right? Because this is a linearly independent subset, and we know that this linearly independent subset cannot have a size greater than that of the dimension of the vector space it is in, right? Okay, and once you have this object, then we can conclude that this has dimension, so this clearly has dimension W plus 1, right? And is obviously strictly less than the dimension of W. Okay, so this is how you get this how you get this final statement over here. Okay, so that is the proof of this corollary over here, that W is a proper subspace. If W is a proper subspace of finite dimensional vector space V, then W itself is finite dimensional, and the dimension of W is at most the dimension of V. Okay, so that is the corollary. Corollary 2 says the following. So if in a finite dimensional vector space V, every non-empty linearly independent set of vectors is part of a basis. Right, I mean, this is basically just stating theorem 5 again, right? That you take any set of linearly independent vectors and you can complete them. You can complete the basis, right? Using these, which is basically what theorem 5 was saying here. Right, you take a subspace and then you take some linearly independent subset of W, and this will form the vector space. So it's essentially just a restatement. Okay, so this part is fine. And corollary 3 is saying what? The corollary, okay, so this is the third thing that we wanted to quickly cover. Right, so let A be an n cross n matrix over the field F, and suppose that the row vectors of A form a linearly independent set of vectors in Fn. So A is some n cross n matrix, and the row vectors we are writing as alpha 1, alpha 2, and so on. Okay, now if alpha 1 to alpha n form linearly independent vectors, then A is invertible. That's what we are saying. Okay, and this is more or less just a repackaging of standard things. So suppose that alpha 1 to alpha n are the row vectors, right, like we've written over here. And suppose W is the subspace of Fn spanned by alpha 1 to alpha n. Okay, so span of alpha 1 to alpha n is what we're writing as W. Since alpha 1 to alpha n are independent, the dimension of W is n, right? So dimension of W is n, because there's n vectors, they're linearly independent and they span the vector space. Alright, now corollary 1 shows that W equals Fn. Okay, because otherwise from the corollary rate we have that if W were indeed a proper subset, then the dimension of W could not be n, right? Because we just argued this, that for any, if you have a proper subspace, then the dimension will be strictly smaller. And that's what corollary 1 said. Okay. So this is fine. So we already have concluded that since there are n row vectors that are linearly independent, the dimension of W must be n. And from the corollary, we also know this implies that W has to be the same as Fn, because W is a subspace but has the same dimension as Fn, right? So dimension of Fn is also n, right? Which is what we were calling V in the previous example. Okay, so now therefore, what does that mean? It means that there exists Bij in the field such that epsilon I, so the standard, so this is at the ith entry, this is what we were calling epsilon I. So it's saying that epsilon I, so it's basically some vector in the field, the standard basis vector to be more precise, can be written as a linear combination of alpha j's, right? Because W is a subspace and alpha span the space. And one can do it for each of these vectors. That's fine. And basically if you expand this, right, this is written in terms of vectors, but if you expand it in terms of matrices, so if you write okay, this would give you BA time is identity, and identity is just this matrix, right? B is the matrix that we get by using Bij as the entry, and A is the matrix of alpha 1 alpha n, right? So that is just how we had defined A, right? Okay, so we get this, and what does that mean? Well, that means that it is invertible, right? So invertible meaning, and we actually find the inverse. So there exists P such that PA is identity, right? So and then from properties that it's enough to have just the left inverse because it's a square matrix and things are fine. Okay, so that is all I wanted to cover today, and I think next time we'll look at theorem 6 and try to finish the section. Okay.